We have to consider a satellite in orbit. Well, an orbit is a type of circular motion that's going around and around the planet. And if there's circular motion, there has to be something forcing it to go in a circle, because the natural motion is in a straight line. Now, in the previous question, it was the friction force between the tyres of the car and the road pushing the car, forcing it to go in a circle. If you're in an aeroplane, you turn the rudders, so they push against the air, and the air pushes against the aeroplane, and that causes it to go in a circle. What about a satellite? There's nothing to push against. There's no atmosphere, there's no surface out there. What's giving the centripetal force? Well, that's Newton's genius, was to realise that gravity is in fact universal. It applies everywhere, not just on Earth. So the gravity is what is providing the centripetal force. So there's not two different forces, centripetal force and gravity. There is gravity, which is providing the force necessary for it to go in a circle. So what we can say is that those two things are the same size. So the centripetal force equals the force due to gravity, which gives us mv squared on r equals big G m1 m2 on r squared. Now, one of those masses is a satellite. Let's call that mass 1. That's going to cancel. So that gives us v squared on r equals big G. Now, the mass that's left is the mass of the planet, or the central body, whatever it is. It's a big object, so we're going to give that a capital M divided by r squared. We're going to multiply both sides by r just to get rid of that denominator. So v squared is big G bm on r. Therefore, v is going to be equal to the square root of big G bm on r. So there's our orbital velocity formula. Not something that we're given, something that we need to be able to derive. Big G big M on r. Now, of course, because we're taking the square root of that, strictly speaking, it's really not a velocity. It's changing every second as it goes around in a circle, as we saw before. It's really more technically an orbital speed, but that's what we've been asked to do, to find out how fast it's going to be going. So let's have a go at doing this question here by doing the summary step. Okay, so we've been asked, so the mass of the satellite, which is M1, is 400 kilograms. You've probably already worked out that that's irrelevant. I'm not going to need to write that one down even, because it got cancelled out. There's no M1 in my formula here. Now, the mass of the Earth is 6 times 10 to the 24 kilograms, always making sure that everything is in the correct units. Now, the radius is going to be equal to the radius of the Earth plus the altitude, how high above the Earth it is. The 6.738 times 10 to the 6 metres, converting that from kilometres into metres, plus 2 times 10 to the 5 metres for our 200 kilometres of altitude above it. So our radius is going to be the sum of those two things, which is 6.738. 10 to the 6 plus 2 by 10 to the 5. Okay, it's going to come out at 6.938. 6.938 times 10 to the 6 metres. There's my radius. Okay, so now we're getting somewhere. We've got our head around the question. We've done our summary step. We've got our law, which we've just derived before. So my orbital velocity is going to be equal to the square root of big G, big M on R, which is very simply 6.67 times 10 to the minus 11. That's big G times 6 times 10 to the 24 over 6.938 times 10 to the 6. And I want the square root of all of that. And let's see if we can do all of that. So I want the square root of 6.6710 to the minus 11 times 6 by 10 to the 24 divided by 6.938 10 to the 6. You can probably do this faster than I can. Finish off my square root sign, and therefore my velocity, my orbital velocity is 7594 meters per second, equals 7594 meters per second. So it's around about 7.6 times 10 to the 10 to the 3 meters per second. That's how fast I'd have to be for whatever mass of satellite, because the mass 1 cancelled, it didn't really matter. However fast the satellite is 200 kilometers above the surface of the Earth.